shouldn't have started this setting. Alright. Alright, so let me see if you're still hearing me. You guys are still hearing me? Clear? Okay, great. Alright, so it automatically switched. Alright, so we're going to start looking at some of the electrical quantities and electricity, electromagnetism. That's what we're going to be focusing on. This is working good. Alright, so before we look at the questions, we can just browse through this first. So, just a reminder about if we have charged particles, we call them point charge, we can show the electric field around it. So remember, when it comes on to electricity, remember that the convention is what is used to indicate the movement of charge. So the convention is that it's the positive that moves, right? Positive particles that move. Yeah, so that was the conventional or old belief. So most of physics uses the conventional. We know in reality things like the electrons that tend to move, like in wires, it's the electrons that move. It's really the negative. But conventionally, it's really supposed to show the movement of the positive. So anytime you're drawing electric field lines, the arrows on the line should be pointing away from the positive and towards the negative. Alright, so the arrows just indicate where would a positive go if you were to place it in the field. Alright. Of course, opposite charges attract. So if you put two charges beside each other of opposite charges, then you see how the field lines will look. If you put like charges together or close together, it's going to repel. So you see that area there, area between, which is clearly showing that repelling action. And then the last one down here is showing if you have parallel plates, one positive, one negative, you end up with this uniform looking field lines going from positive to negative. So remember to recall those. Alright, another concept in electrostatics is charging an object. So you can charge an object by friction, so that's direct contact, and we can charge by induction. So you should be able to explain, so like this, this image where you have a plastic rod being when you rub the plastic rod with a cloth, if the cloth becomes negative and the rod becomes positive, it's an indication that the electrons move from the rod to the cloth. So it's the electrons. When you're doing an explanation for this topic, you'd have to talk about the movement of the electrons. Alright, so that's charging by friction. So electrons jump from one material to the next, one object to the next. Whereas charged by induction now is where you have a neutral object. So you'd have initially a neutral object where the charges are evenly spread about, so not divided as you're seeing here. And then you'd bring a charged object close enough to it that will cause the electrons in the neutral object to respond to it. So if you bring a positively charged object close to a neutral object, the electrons closest to that rod, or the electrons will migrate to the side that's closest to the rod. So alright, and if the electrons migrate closest to the side there, that means that the other side is going to become positively charged. Alright, if you bring a negatively charged rod there, the opposite is going to happen. Electrons are going to be repelled by the negatively charged rod, so you're going to have positive on the side closer to the negative rod and negative running away. So those are some concepts should be familiar with. Should also know dangers of electrostatics and potentially some uses, because it has some useful applications. So dangers would be things like lightning strikes and when pumping gas, you can have this kind of discharge happening. So you want to prevent this type of discharge happening when you're pumping gas. You don't want to start a fire that way. So alright, so let's zoom in a little bit and look at some Alright, so the first one is to define the term electric field. So with the diagrams that we saw earlier, when it comes on to electric field, you see those lines represent the area around the charged object where you would experience an electric force. Alright, so you have electric field, you have magnetic field, so you can apply it to both situations. So it's the electric, sorry, it's the area around the charged particles. Alright, hold on. Who is this now? Right, so it's the area, electric field is the area or the field. Probably don't want to use the word field again. Around, surrounding a charged particle. Where an electric or another charged particle would experience a force, or where you'd experience an electric force. Um, Alright, sorry about that. Stay there. Look at this diagram. So I showed you the diagrams earlier, and we know the convention in terms of movement, conventional conventional flow, similar. So if they tell you have two charges here, A and B, state the type of charge at object A, what would you say would be the type of charge at object A? It, no man, it's the electrons move, but remember, you have to kind of discard that for most of physics. So in convention, so if you saw the image, I don't have to go too far. If you saw the images earlier, the the electric field lines, you'll see that the arrows are basically telling you if you put a positive charge near these objects, how is it going to behave? That's basically what the lines tell you. Alright, so it shows you the direction of positive point charge, or how a positive charge will move. So conventionally, we know that conventional current deals with the flow of electricity from positive to negative. It's the same way. All right, so in reality, as we say, it's mainly the electrons that move when electricity is conducted, but even though that's the actual case, you have to use the convention when you're doing these. All right, I think the only case, as I said, the only case where you'd have to you'd have to talk about electrons moving is if you're talking about um, charging, charging by induction or charging by friction. All right, everything else you use conventional flow of current. All right, so if we're using conventional flow of current for this diagram, A would have to be which one? So A would have to be positive because the arrows are pointing away from it, right? And B would be negative since the arrows are pointing towards it. All right, so that's have to stick with the convention. All right, and then you have part B now, which says explain how a polythene rod, when rubbed with a fur rubbed with fur, becomes negatively charged. I talked about this a little, something similar to this earlier. So what's happening here? How would the polythene rod become negatively charged? So, alright, so the electrons, some of the electrons leave the fur and go, go on to the rod. Those say go to the protons, says that might, yeah, that's not really true. Um, but yes, it moves to the polythene rod. So the polythene rod would be initially neutral, which would mean it would have equal number of positive and negative charges, or in terms of the value. Um, so the only way it would could become negative is if it's gaining electrons. The material is gaining electrons. Alright, so that's charging by friction. So that asks it to um alright, we can do this one quickly as well. Um so we talked about electric field, so now if we look back at that one. Alright, so figure 8 shows a positively charged sphere which is attached to an insulated stand. Draw arrows to indicate the pattern and direction of the electric field in the region surrounding the sphere. Alright, so that shouldn't be any problems. It should be basically spherical or in a circle. There's the lines going out and with the arrows pointing out since it's positive. Alright, so it should look similar to the point charge um, diagram. Alright, a smaller uncharged sphere Q is suspended by a cotton thread and brought close to the positively charged sphere as shown in figure 9. Draw the distribution of charge on sphere Q. Okay, on sphere Q. So Q is brought close to this object. What's going to happen? What are they testing here to see if you realize it's going to happen? What's going to happen when Q is brought close to this bigger sphere? The electrons would move where? So, no. The electrons are going to move, but it's it's not going to move to that bigger sphere unless it's touching it. So if it eventually touch it, then you can talk about the electrons moving. Right, so all it does is it creates a separation. Alright, so this one would be charging by what then? What's the other type of charging? So we just looked at friction, charging by friction. What was the other one? All right, so charging by induction. All right, so in induction, you're not physically touching the object, or you're not bringing anything in contact with the material. It's just based on proximity. All right, so the closeness of it. So your diagram should look something like that on Q. So on the smaller Q, you should have a distribution similar to that, where the negative is closer to the positive sphere and the other side would be left positive. All right. All right, so not a problem. All right, so an earth wire was briefly brought into contact with sphere Q as shown in figure 10 and then removed. Describe what happens in the wire and state the final charge on Q. So remember how, so it is a follow-up from the previous question. Remember what would have been on that side where the wire is now connected. So what do you think will happen if we should now connect that side? So let me draw. Any ideas? All right. All right, so we have the positively charged sphere. This was the original. And we would have a smaller. So Q, we said that, I'm going to try it a little closer. So the negative charges in Q would be closer to the positively charged sphere. Alright, and you'd be connecting a wire down to Earth. So think about it from this aspect. What charge is the Earth? So I would say Earth or ground cinema. What charge is going to be? down here? What charge down here? No, not positive. Not positive. Yes, go ahead. Yes, so it would be neutral. So Earth is neutral. All right. So now we have a wire that's being used to connect Q to Earth. So if it's neutral, what does neutral would mean that? What would it mean in terms of the particle, the charged particles that's there? Wouldn't it just mean that we have positive and negative? So evenly distributed. All right. But because it's connected to the positive side of Q, what's going to happen is that the electrons is going to be attracted to it. So it's going to have the same effect as if you, all right, let me just use the sphere. It's going to have the same effect as if you connected a wire to the positive sphere. Same effect. The electrons from Earth are going to move, travel up the wire because it's going to be attracted. It's going to be attracted to the positive charge on that side of the wire. All right, so picture the electrons moving from Earth to Q. All right, so before there was a wire, before the wire was there, what would be the charge on Q in this state, in this current state? What's the charge of Q before the wire situation? Right, so it would have charges zeros. So even when you split the charges, the negative to one side and the positive to one side, it's still zero because it still contains an, yeah, right, same amount at each charge. But now if electrons are now being attracted to the positive side, what's going to end up happening to Q? Right, so it's going to become negatively charged because now you have more electrons in Q than you do have, or more negative charges than you do positive charges. All right, so in these type of questions, just if they talk about connecting charged particles, just think about how the electrons would move, what direction the electrons would move, right? And that will help you to decode what they're asking. All right. I don't know why it's not. All right, next one. Let me bring this up some more. All right, so this one shouldn't be a problem. So we should know the equations for these. Um, the battery in an electric car can be charged by passing a current of 11A through it. calculate the charge stored in the battery after 8 hours. Alright, so easy stuff here. And somebody the chemistry say electrolysis fresh in the mind. So charge, how do you calculate the charge? Yes. Alright, so Q is equal to IT, so make sure you write the equation. Yeah, go ahead. Alright, so this is 8 hours. Alright, so how do you convert the 8 hours? Eight by 60. Well, that's so like I convert to minutes though. Okay, so let's do it one time, man. So 60 or 60 times 60. That's like, uh, so that, what is it? Yeah, man, talk. 28,800. Alright, so that's the charge. Alright, so 1 mark for stating the formula, 1 mark for doing a conversion, and then another mark for substituting the values and your answer. So that's how they would break down the marks for that question. Alright, calculate the resistance of the battery given that the voltage is 220. Calculate the resistance. Alright. So which equation could we use? Which equation? Yeah. So V equals IR. V equals IR. So that means we know the current, so we can transpose. So R is going to be, what's going to happen when we transpose that equation? What is R? Resistance. Alright. I remember what V was, so what's V and what's I? So 20 ohms. All right, great. All right, so let me look at this one. Sorry, wasn't sharing. All right. All right, so you can use this setup to test whether a conductor is a conduct whether material, sorry, is a conductor or insulator. So, mhm, right. So you'd use the materials to complete the circuit. You turn on the switch and see if it lights up or not. Yes. Yes, yes, yes. All right, name one material which is an electrical conductor. All right, iron. So you could list a barrage of especially metals, so copper or whatever it is. What about insulator? Plastic. All right. Or wood or something. All right. So here, oh no, that's it. All right. On the diagram in Figure 8, mark the direction. Oh wait, where's Figure 8? Oh, sorry. There's Figure 8. So mark the direction of electron flow. So what would be the direction of electron flow? Alright, so no, no, yeah, 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 but it would have to be. It would have to be the clockwise direction in this case. So negative to positive, because they specifically identify the electron. They said they literally they never said current, direction of current, they said direction of electron. So because they said the word electron, then they can't use conventional because of that. Alright, so be careful with that. So if they say electron, you have to do the regular way, the actual thing. Alright, so here we have a circuit, and they want us to do some calculations. So let's see if you remember this concept. So I have this circuit. They want us to calculate the ammeter reading, which is another way of saying, of asking what do they want you to find. Current. Alright, so alright, so, okay. So the rate of flow of charge in the circuit. Alright, so they want you to calculate the first one is calculate it when this thing is open. So visualize it. What's the significance, or what's going to happen when this circuit here is open? So if the switch is open, current will not flow through that 3 ohm resistor. Right. Because when it at that junction, it wouldn't need to split, or it can't split because it only has one way to go. So what equation would we be using to determine the current here? What equation would we be using for current, to find current? Okay, so you're using the same V equal IR equation. So you're just transposing for current. So I would be equal to